Yes, so thank you everybody for joining us. Thank you very much to Andrew. So I guess Andrew doesn't really need an introduction, but I'll do a very short one. Andrew has done a great deal for the open community. He leads Open Mind, which I'm sure he'll talk about more in this talk, but it's a great way to share data that otherwise could not possibly be shared. In addition, he wrote a textbook on deep learning. He teaches courses on machine learning. If I remember correctly, he even gave congressional testimony at one point. And by the way, he also finished a PhD this year. So thank you very much, Andrew, for joining us.
Awesome. Glad to be here. And thanks for having me. Shall we jump in?
Please.
All right. So this is a new talk, new material. I have not given this talk before, so bear with me on some things, but also fresh stuff. So that always good fun. So I'm gonna go ahead and share my screen. So we are gonna roll through some slides. Can you see this? Okay. Oh, there we go. All right, brilliant. Is that still full screening or is that too small? Yeah, it's good enough. Okay. Cool. So talk about the future of AI infrastructure. So I want to talk about sort of what the next level of tools and techniques are going to be. And the first kind of problem I want to start with is that just the AI industry moves crazy fast, and it's really hard to anticipate where it's going to go next. But it can be really important to anticipate where it's going to go next when, for example, you're planning your career, right? So someone already asked me a moment ago, like, how to get a job at DeepMind. I would say a different way to respond to that is one of the most important things you can do is predict what's about to be really valuable and become an expert in that thing, if that makes sense. So that you're like the great hockey players, Wayne Gretzky said, don't skate to where the puck is, skate to where the puck is going to be. Because if the whole industry is about to want a certain type of talent and you have a year of extra experience on that particular skill set, that puts you in a position to be in really strong demand, right? So, but what's really difficult about that is it's hard to predict where AI as a field is going to want to go. And so we're going to talk about that for a minute. And the way that we're going to talk about that is first by looking into the past. Where has the AI industry sort of gone in the past? What have been the big moments? And then we're going to look for patterns that can indicate what comes next, if that makes sense. So again, I guess for, who was it that asked me that question just a moment ago? It was Milan. So Milan, pay attention to this, because if you're trying to find a job or a position or otherwise advance your career, being able to make a really good prediction here can make all the difference. Okay, so let's start looking at individual things. So this first one on the left here, this is, oh yes, first we'll do a couple primitives. What is an AI breakthrough? So an AI breakthrough is a significant increase in AI capability, I would say, often accompanied with press releases and excitement and fanfare and ticker tape parades or TechCrunch articles. But if we're going to ask this question about what makes an AI breakthrough, we first need to ask what makes AI capable in general. What is the engine that drives these big breakthroughs? And for that, we're going to look at something that is, I think, a little bit underappreciated, which is called statistical learning theory. Statistical learning theory tries to, is sort of the science of why AI gets smarter, if that makes sense. So let's look at statistical learning. Got a heart for that. Yay, statistical learning theory. All right, this is, we're not going to go super deep in this. I'm not going to show you formulas. We're just going to do the very, very, very basics. So the first thing to know about statistical learning theory is it's dependent in part on the number of samples, right? So statistical learning theory will tell you that the more samples that you have, the smarter your model can be. Now, I want to grossly oversimplify this for a second with an example. So imagine the MNIST data set. I think it's like, oh yeah, there's like a thumbs up thing. I assume everyone here has at some point tried the MNIST data set, right? Super popular, yep. Now I want you to imagine a new MNIST data set that is so big that it has every possible permutation of pixels in the input data. So the MNIST data set, it's like 60,000 images, right? But imagine that, if it's, 784 pixels? Imagine if you had every permutation of possible input pixel and it was labeled, right? The thing that statistical learning theory would tell you is, like, at that point, you have, in a way, a perfect classifier. Why? Because no matter what handwritten digits someone can give you, you can look in the data set, and the data set's going to tell you what image it is, right? But if you go to like, even if you did binary, it would be like 2 to the power of 784, right? That would be such a huge, it's like, more than the number of grains of sand in the universe or something like this, right? But even for MNIST, it would be a huge, huge, huge data set. So the problem in machine learning and learning theory tries to solve is say like, okay, let's say you started removing, you didn't generate all those images, and you removed them and you removed them, and you got all the way down to just 60,000 images. How can you use a model to fill in the gaps of all the images that you don't have? If that makes sense. So that when you present a new one, you can fill in the gaps of these missing pieces. But this is where the number of samples really matters, because the more samples that you have, the more information you don't have to infer, you don't have to look up because you already know it. And the fewer samples you have, the more you have to infer, and the more you have to carry on a second principle of learning theory, which is sample complexity. Sample complexity refers to how efficient your algorithm is at turning samples into accuracy. Right? So if you have an algorithm with really phenomenal sample complexity, a very small number of data points can get a really high score on your test data set. And if you have an algorithm that has terrible sample complexity, then you have to have a huge number of training data points in order to even get small increases in accuracy, right? First big lesson, this was one of the biggest lessons I ever learned in the machine learning field. When someone told me the point of machine learning research, one of the ways that you could describe it in one sentence is, all the papers at NeurIPS, all the papers at ICML, going all the way back to the beginning. One way to describe in a single sentence what the purpose of all those papers is to improve sample complexity, right? Now, there are some papers that also add data sets, right? So that would be improving the number of samples. But in terms of better algorithms, better optimizers, better regularizers, better model weights, all this kind of stuff, the thing that we're trying to do is say, given a certain number of data points that we have, how can we get better accuracy? How can we improve the sample complexity? Okay, this is really, really important, right? And the reason that it's important is that when we look at, say, the napkin math, we'll see that that AI capability is this sort of back of a napkin. How many samples do you have? What is the sample complexity of your algorithm? That's how strong your model is, right? From a statistical learning theory perspective, right? And compute unlocks more samples. So when we ask, like, what's the point of GPUs? Why are GPUs driving the AI revolution? It's allowing us to amplify the number of samples that we can work with. We can scrape the whole internet or train on, video games for days and months and all this kind of stuff, right? But from a statistical learning theory, what's actually happening is we're able to work with more samples, and that's driving up AI capability. Okay. So let's go back to our timeline and start looking at this timeline from the perspective of sample complexity, right? And what we're going to see is the nature of each one of these breakthroughs, and that's going to allow us to start to make predictions on where the next breakthroughs are most likely to come from. And then people like Milan can make good guesses on how they would plan their career, right? Because if you can anticipate where the breakthrough is likely to be, then you can position yourself there as a future employee of top AI places or researchers or academic institutions, this kind of stuff. Okay, so let's do it. So the first one I want to talk about is in 2009. So Reina Madhavan and Andrew Ng published a paper that trained on a GPU for the first time, right? They trained a model with 100 million free parameters, really, really big deal. This kicked off a huge amount of innovation in the deep learning revolution, because prior to this, neural networks were very, very difficult to train, right, on sort of multi-threaded CPUs. So really big deal. So we're going to call this more compute, right? So more compute, and that advanced the field. The next thing, innovation I want to point out is the ImageNet data set, 2010, right? So the ImageNet challenge kicked off. This data set was added to a couple times later, but this is sort of the big kickoff. You can see this website here. So that's more data, right? Two big innovations. And then we have one of the most famous innovations, which is, quote, the ImageNet moment, right? And the ImageNet moment was the first time that, Alex Krizhevsky and Ilya Sutskever and Jeffrey Hinton combined GPUs with the ImageNet dataset with Dropout, right? Dropout was this really powerful algorithm. Maybe some people, Dropout, it used to be this thing we always talk about all the time. Now, lots of other things to be distracted by. But for this, I'm going to say better sample complexity, right? Because Dropout allowed the model to get higher levels of accuracy with lower numbers of samples. Okay, so you see this trend that we're going on. So we're kind of going from big breakthrough to big breakthrough, looking at what was the class, what was the type of breakthrough that it was. Okay, so now Word2Vec. Does anyone remember Word2Vec? Do people talk about Word2Vec? Anyone? Word2Vec was so cool. Remember the word king minus man plus woman equals queen? This is like mind-blowing stuff, right? Okay, so Word2Vec came out in, what was it? What did I say? 2013. And in Word2Vec, you might be tempted to also call this a sample complexity improvement. But let's read this abstract for a moment. The recently introduced skipgram model is an efficient method for learning high-quality distributed vector representations that capture a large number of precise syntactic and semantic word relationships. Whew, there's a sentence. In this paper, we present several extensions that improve both the quality of the vectors and the training speed. By subsampling of the frequent words, we obtain significant speed up and also learn regular word representations. The core idea of this paper is training faster. If you look at the architecture of this paper, this took a vanilla recurrent neural network, RNN, and stripped out a bunch of the complexities. It removed the nonlinear layer in the middle. It came up with these approximations for the output layer that actually damaged the model's ability to learn, less expressive. But it allowed Thomas Mikolov and team to write a C file that could train on like 1 trillion words in like 10 minutes. They could train on a huge amount of data. And I didn't first realize this when I read the paper, because like everyone else, I was like, oh, the algorithm is amazing. Word2Vec is super smart and it's doing the crazy thing with the words and it's figured out language. But I was at ICML in 2015. And you know how they say in conferences, you go for the talks, kind of, but the real conversation, the conversations in the hallways is where all the really juicy stuff is at these conferences, right? So at ICML in 2015, I had my first moment like that, where I happened to be, literally, I wasn't even in the conversation. I happened to be walking down a stairwell behind Thomas Mikolov and someone else he was talking to very loudly, right? And you know what he was talking about? He was talking about this paper and the motivation for it. And what he said was that in building Word2Vec, what he was trying to do was simplify the architecture so they could train on way more orders of magnitude data than anyone had ever done for an RNN. Right? And so if you look at the implementation, it does a bunch of dangerous things with threading. It's a bunch of threads all accessing the same memory, right? In a way that would normally corrupt the weights, but it works out because of the nature of machine learning. It doesn't have to be exactly if you override a weight, it's not the biggest deal. And even though this model is strictly speaking weaker than a vanilla RNN, because they're able to train on so much more data, an amazing new property came out. And the point that I'm trying to make here is that even though this looked like an algorithm innovation, and it was an algorithm innovation, the strategy that was being employed was actually more data, right? That's what caused Word2Vec to be so exciting. All right. Now let's keep going. DeepMind and Atari, playing Atari with deep reinforcement learning. Such a cool paper. I will never forget the first time that I saw it and saw that demo of the little paddle and the ball bouncing around, all this kind of stuff. We present the first deep learning model successfully learn control policies directly from high-dimensional sensory input using reinforcement learning. The model is a convolutional neural network trained with a variant of Q-learning whose input is raw pixels and whose output is a value function estimating future rewards. Look at this. Okay, convolutional neural networks have been around for 30 to 40 years. 30 to 40, the 80s, I think. So I guess, what year was this? Maybe 20 years. Q-learning had also been around. That's in reinforcement learning. You know what this paper had that was super, super new? An infinitely large training data set, because they're training on games. And in a game, you can train forever. So I think, even though there's great algorithmic work here, I think that the workhorse, the big strategy is actually more data, right? Or at the very least, there is a very strong data story underneath the Atari breakthrough. AlphaGo, same idea, right? Now, there's some really cool algorithmic work here. The Monte Carlo tree search, undeniable, very interesting innovation, right? But also, infinitely large training data set. People were not doing this before. People were like, let's grab a chess data set from a bunch of grandmasters and try to learn like grandmasters do, right? But there weren't that many grandmasters games to play. You know, the data set at the time was like 25 million games, something like that. Someone had gotten from an online game or something like that. But the innovation here, right, could train, against itself for a really long time, which means you have an infinitely large data set to come from. So from a statistical learning theory perspective, it's more samples, right? And also some improvements in sample complexity. Let's keep going. Let's talk about the transformer paper. Attention is all you need. I also remember exactly where I was standing the first time I read this paper. Genius paper, but what was its strategy? Let's read the abstract. The dominant sequence transduction models are based on complex, recurrent, or convolutional neural networks that include an encoder and decoder. Emphasis there is on the word complex, right? The best performing models also connect the encoder and decoder through an attention mechanism. Attention is around. We propose a new, simple network architecture, the transformer, based solely on attention mechanisms, dispensing with the recurrence and convolutions entirely. What are they saying? They're saying they're throwing away complexity. These big complex things you were doing before, we got rid of them, right? Experiments on two machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Ergo, simplify the model, train it on more data faster. See the theme? It's the same strategy as Word2Vec. Yes, it's an amazing algorithm, but the algorithm was developed by taking a more complex algorithm and stripping out the complexity so you can train faster. Why would you want to train faster? Why would you want to train bigger models? To train them on more data, right? So the other way to look at attention is all you need. Is it like, instead of an LSTM that had an infinite context window, it should be able to take in data from the eternal past and think about it together and put it all together. We're going to say, nah, let's have a discrete context window. Let's not have recurrence, right? Let's not have convolutions. But with this simple context window, we can pack it super heavy on GPUs and train a massive model on a ton of data, right? So I would argue that the big workhorse making transformers better than what was before, right? The reason this is crushing LSTMs, more data. More data. However, when this paper came out in 2017, it didn't have the immediate explosive fanfare that you might expect now. It's actually quietly released. It was a big deal. It popped around circles. It was an influential paper. But it wasn't clear that ChatGPT and Gemini and this kind of stuff was going to come from it just yet. That didn't happen until GPT-1 and 2. Let's take a look at GPT-1. Natural language understanding comprises a wide range of diverse tasks such as textual entailment, question answering, and a list a couple more. Although large unlabeled text corpora are abundant, labeled data for learning these specific tasks is scarce, making it challenging for discriminatively trained models to perform adequately. We demonstrate that large gains on these tasks can be realized by generative pre-training of a language model on a diverse corpus of unlabeled text. AKA, this is a strategy for getting way more data. Self-supervised learning, right? Followed by discriminative fine-tuning on each specific task. What they're saying here is that they're using the same architecture that came a couple years before. And that architecture, the transformer, was built to have more data, but the initial release of the paper didn't necessarily actually add it to more data. So what they're coming back now and saying, hey, this transformer can process lots of additional data. Here's a really cool strategy to have tons of additional data. And guess what? A big jump in performance fell out of the model. There wasn't a big algorithmic change here, right? But this created so much excitement because it was a huge increase in capability. It was an AI breakthrough, a big jump in capability. And why? More data. Let's look at GPT-2. Natural language processing tasks, such as question answering, machine translation, and summarization, are typically approached supervised learning on task-specific datasets. We demonstrate that language models begin to learn tasks without any explicit supervision when trained on a new dataset of millions of web pages called web text. GPT-2 is an innovation in a huge new dataset. Sorry, I know I'm repeating myself over and over and over again, but do you see how this works? There is a really strong pattern for where AI breakthroughs come from. It's data and model complexity and more compute, right? But look at the really common theme here. Now, GPT-3 did not make big data claims, right? I would argue that this is a little bit of an exception to the rule. The culture changed on how these things were being talked about, and we don't necessarily know everything about the data set that it was trained on. We'll skip that for the moment. InstructGPT. Also about the data. InstructGPT. So this is an approach through which you have new types of people annotate new data about what you want a model to behave like. It is a data acquisition strategy. So Let's revisit a couple of these. More compute. Why do we want more compute? I would argue the reason why we want more compute is capacity to train on more data, right? Even model size can be viewed as a data strategy. Why? Because if your model is too small and you try to cram a bunch of data into it, it will underfit, right? It's almost like the size of your model is like the size of the bucket that you can use to hold information, right? So if you have bigger computers, you can make the bucket bigger, and now you can pour in more data. So if you look at what GPUs kicked off here, this 13-year, 15-year revolution, it was like GPUs allowed our buckets to get way bigger, and then there's all these different strategies to take advantage of them, right? To be able to cram more information into these things, right? Let's revisit another one of these. I want to revisit this GPT-3, more compute to handle more data. This was closely linked with the idea of the scaling laws. I think everyone here, folks here, heard the scaling laws, the idea that you make the model bigger and the model gets more accurate. From a statistical learning theory perspective, the scaling laws, it's not that they don't make sense. They make sense in a very particular way. If you train a model and you make the model big enough to hold all the data, right? You get a really accurate score. So you fully maximize the number of samples and the sample complexity your model can do. And then you just make the model bigger. You know what happens? You overfit, right? Machine learning 101 kind of stuff. So what does that mean if you make the model bigger and it gets more accurate? What that means is the previous model was underfit. It was too small, which means when you're pouring data into this bucket that's too small, a bunch of stuff is flowing over the top and not getting saved in the model. Does that make sense? The model's having to throw away stuff during training. So then when you make the model bigger, it can hold more information and performance and accuracy goes up. But that's why the strategy eventually runs out unless you have more data. Does that make sense? Because if you just make the bucket bigger and bigger and bigger and bigger and bigger, eventually you are going to overfit and you are going to need more data. That makes sense. So this is why I interpret the scaling laws, and I interpret things like GPT-3 and 4 and these kind of stuff as, great that the model gets bigger. Agree that's important. Statistical learning theory tells us how to interpret that. I want to look at another one. More compute. Between 2013 and 2016, between when DeepMind did Atari and when DeepMind did AlphaGo, they were acquired by Google. How did that change their level of compute access? Boom. You know what I mean? From being a startup in London to being a wing of Alphabet. And I want to look at one more. This is a big one. I want to look at the ImageNet moment. Because a minute ago, I said that this was dropout. And the dropout's about better complexity. And that's true, right? Better sample complexity, right? The model can get a higher level of accuracy with a smaller number of data points. But I want to recast this story for you in two ways. First, what does dropout do? Dropout adds noise to the inputs and the internal representations of a model. When you add noise to the inputs of a model, like the input data, the first layer of a model, what are you doing? In a way, you're modifying the training data set. You're making it bigger. And if you think about the example I gave a minute ago of imagine you had MNIST that was every possible MNIST image in the universe, right? And you start removing them, you try to start filling in the gaps. Dropout is a way to remove things and try to learn how to fill in the gaps. Do you see what I'm trying to say? It is making it harder to memorize the data set by making it more diverse. And if you now picture in your mind, by infinite data, what I meant was every possible permutation of input pixel. So it actually wouldn't be infinite; it would just be very large. Good question, Milan. Sorry, I lost my train of thought. Now imagine that you are one of the internal weights inside of a neural network. Like you are one of the weight matrices. So neural network is like a big stack of matrices. Picture yourself as one of those weight matrices, right? And you're trying to learn. And data's coming in and learning signals coming in at the top, right? Dropout is adding noise to both sides. So from your perspective, you're going to see the same sample view. Dropout is going to make it look a little bit different. So from your perspective, it actually is making the data set bigger. The dropout itself has a increase the data like property. It has a data augmentation like property. Second, if that's not enough to persuade you that this is actually a data-driven story, right? Second thing I'll point out is that the reason this paper was big was not just because it made neural networks smarter, because it made neural networks smarter than probabilistic graphical models, than the Bayesian approaches. That's why people were excited. Now, I will tell you right now, the big question at that time was like, wait a minute. But Bayesian approaches have better sample complexity. Why are we leaning into deep neural networks? These probabilistic graphical models, they do this. You can set up all this internal structure that helps with the learning. Check out Daphne Kohler's course on Coursera. It's like one of the best courses on this. If you want to check this out, they have better sample complexity, but it's really hard to run them on GPUs. And if you look at the history, in 2009, all this huge compute capacity came from gaming for AI. So all of a sudden, there's this huge increase in the number of samples that deep learning models can process. The PGMs had a really hard time following that and also taking that advantage. Simpler models. The modeling innovation, the ability to pump more data through it, is a huge tailwind. So I would argue that across this, the big workhorse on driving the next big breakthrough in AI is consistently asking the question, where is the next big data point coming from? Where is the next big growth coming from, right? Predicting AI breakthroughs is as hard as predicting the next 10 to 1,000 times increase in data, right? 1,000 times more compute means 1,000 times more data. Being able to use dropout to randomize whatever data you have, right? That's orders of magnitude more training signal for you to be able to work with. Being able to train on video games and have an infinite number of samples is many orders of magnitude increase in the amount of training data that you can work on. Scraping the entire internet is orders of magnitude more data than you're able to work with before. Yes, algorithms happen along the way, but even the biggest algorithmic breakthroughs, the transformers, the word-to-vec, were data stories, right? They were tearing away things that prevented the model from being trained on more data. They're simpler algorithms than what came before. But because they're simpler, even deep learning itself is simpler than the probabilistic graphical models, right? Less expressive. But because we can cram more data through it, it allowed us to have big breakthroughs, right? And there's a bunch of things I didn't even talk about. GANs. What are GANs? You have one model that generates training data for another model, right? What is reinforcement learning using human feedback? Hiring people to create more data, right? What is distillation? Using a model to create a training data set for another model that is better and higher accuracy. What are the tokenization innovations? A way to augment the input data that goes into the LLM so the LLM is smarter. This data innovations are everywhere. Increases in data, and I'll put in parentheses, or data quality. So tokenizers didn't change increase the data, they changed its ability to be used. Okay, so let's go back to statistical learning theory. There's a bunch of innovations that are about more and better samples, right? And there's also some that are about sample complexity. Attention, undeniably about sample complexity, right? Convolutions, undeniably about sample complexity. Optimizer work like SGD and AdaGrad, batch norm. These are, right? But how do we predict the next AI breakthrough? If we're trying to be predictive, right? Where are we going to look? Now, if all this is not persuasive to you, you're still like, Andrew, but the algorithms are really smart. We're getting faster, better algorithms, right? I want to tell you a quick story. I started, yep, totally, bitter lesson. This whole talk is definitely in line with the bitter lesson. And we're about to make a pivot here. It's very much in line with the bitter lesson. Great call. I started a PhD in 2017. I was very excited. Cohere. So this is being hosted by Cohere. So your chief scientist is Dr. Phil Blunsom. So Phil Blunsom, my PhD supervisor as well. So same guy. Really smart. Cohere is really great. Phil's really smart. All the good things. I was very excited to work with him. At the time he was working at DeepMind, he was leading the language team there, doing language modeling. So I was really interested in language modeling, and that's why I wanted to work with him. And my partner and I packed up all our bags and we flew to the United Kingdom and we got all moved in. And I go to Phil's office and I sit down and I'm like, all right, ready to start my PhD. What do I need to know? I'm like, sitting with the master, right? The person does language modeling at Google DeepMind and like this really amazing paper at Oxford called Teaching Machines to Read and Comprehend, which was really awesome. What do I need to know, right? What is he going to teach me? And the first thing on the first day he told me was, Andrew, everyone's going to want to focus on models, but the real breakthroughs come from data. And I went, huh? Because like, that would make sense. I probably gave the same look to him that some of you are giving to me right now, right? And he had just finished publishing this paper, Teaching Machines to Read and Comprehend, where he took a relatively normal vanilla LSTM and had this amazing new data set from news media, all this kind of stuff that got these machines to do this really, really cool stuff. And not only was he right in the moment and looking historically, he was right about all the biggest innovations that are about to come. Transformers came out that year, the other big GPT breakthroughs and Gemini and all this kind of stuff came out shortly thereafter. He was right. So if you don't believe me, believe Phil, because Phil was right. Okay, so let's go back here, right? We're trying to predict where this stuff's going to come from. Where are more and better samples going to come from? And where is better sample complexity come from? From an algorithm perspective, I was just describing it from a learning theory perspective. But when we translate this to like an economic and political question of how much capacity is there, how fast does that capacity grow, this is actually about data and compute for getting us more samples. So more data means more samples, and more compute means more ability to process samples. Or more sample complexity. And if you want better sample complexity, you need smart people to figure out algorithms that can give you more sample complexity, to develop attention mechanisms, to develop, dropout, or develop whatever these things might be. Now, we're trying to look at where a big AI breakthrough is going to be. We want to see where is there going to be a 10x or 100x increase in one of these three categories, right? Because if there's a big boom in the amount of those things, that would really increase the rate of change, and that could allow for an AI breakthrough to happen. If we look across history, this is what's been happening, right? Okay. So I would argue that talent is really difficult to predict in this way. Why? It grows so slowly. You know how long it takes to train a Jan LeCun or Ilya Sutskever or a Jeff Hinton? Jeff Hinton worked on neural nets for like 50 years. Jan LeCun started back at Bell Labs. The caliber of people that push forward these algorithmic innovations, it comes from a relatively small group, right? Because it takes many, many years to get to the forefront of that learning theory, right? And so if you ask how fast can talent grow, it's like, okay, how many online tutorials are there? How many undergraduate programs are doing computer science? Exactly how many GPUs are available? All sorts of constraints that make creating new talent slow. Like you don't have, but it can still happen. If you guys are like, oh, that means that I can't become top talent. That's not true. You can, over the course of your career, become a very talented AI researcher, but there's not going to be a 10,000 times increase overnight in the amount of talent that's available. It doesn't work that way. For GPUs, we had this huge moment where there's 1,000 times more compute, just like boom, showed up, right? Talent doesn't work that way. So I would say that predicting where the next sample complexity thing is like, okay, there's a handful of people, maybe it grows by 10% per year, and one of them might happen to discover something in any particular year, but it's very difficult to predict where it's going to happen, right? So, but we're trying to predict. That's what we're trying to do. But it turns out that on the data and compute side, this has been the big breadwinner over the last 15 years anyways, right? And this, I think, is going to be more likely for us to be able to predict. So where will we get 1,000 times more samples sometime soon, right? We're trying to predict this. So let's look at compute. We'll come back to data in a minute. So for compute, are we about to get 1,000 times increase in GPU output? Probably not. NVIDIA will release a new card every year. That new card will have, 2 to 4x more power per price, something like that. It will make its way into cloud vendors. I don't see us getting just like this big surprise, right? Maybe there's quantum. Maybe quantum will happen, but maybe quantum will happen for a long time, right? Difficult to say. Increase in GPU concentration. So maybe we don't need a huge new type of computer chip. Maybe we just need someone to just put 1,000 times more of them in one place that everyone can use to train a crazy cool model. That's possible. But I think 1,000 times increase, 1,000 times larger than the current data centers is like if a government just came in and just like nationalized all of it, right? Seems unlikely, seems kind of undesirable. I don't see that being how the next big breakthrough happens. Seems unlikely to me. Quantum finally happening. Maybe, I don't know, possible, could happen. One I'm actually optimistic about, analog computing. So if you look in the history of computing, digital computing, ones and zeros, really, really great for general purpose computing. But the original neural networks that some of the founding fathers, the guys that were at the Dartmouth workshop and stuff like that, were training neural nets on analog computers because they're crazy parallelizable. I don't have time to get into it today. We could do another talk on it some other time, but maybe. But it would take at least a few years of R&D. There's a couple startups working on it. It's a cool idea. I don't see the compute story here, right? I don't see there's this huge, powerful supercomputing happening in gaming, and it can be repurposed for AI. I don't see the story. I don't see how this can come from compute, like 1,000 times more samples. I see compute growth, sure, yeah, still happen, but not like boom, 1,000 times overnight, big breakthrough. What about data, right? What about data? So now we're talking about not samples, but literal data points. Where can we get 1,000 times more data points? Open web scrape. Not sure about this, right? I think we've run out and it's getting called back. This is in the news a lot lately, right? Bunch of companies scrape the internet, and the companies whose website that had are pulling it back. They're putting up paywalls, like Reddit shut down their scraping, and Twitter made it harder for their stuff to scrape. A bunch of news media organizations have set up walls on their stuff and are renegotiating it. So like even the data that was in the internet before to scrape for AI is actually getting smaller. This article, the data that powers AI is disappearing fast, I think is quite well described, right? There's less data available. Even though more data is being produced, it's getting locked down. Why? Because it's valuable and all sorts of things, right? So what about hiring annotators, hiring lots of people? Well, that's pretty expensive, right? Are we going to see 1,000 times the size of the internet show up because we hired a bunch of people? You know how many people that would take to hire? It would take a lot of people to hire, right? Now, is it still worth doing? Are there going to be successful companies in this area? Absolutely. But is that going to be the big breakthrough that changes this stuff? I doubt it. It's not where I personally see the next thing happen. What about simulated data? Can we use a simulator, right? Just like, the games that we played or all this kind of stuff. I think we kind of already did that. We already threw a ton of R&D at simulation. And the problem is, for some problems, for physics problems, I think they work great because physics is this compositional thing where you can cram stuff in there. And you can do sim to real. So for robotics, for physics, I could see this working, right? But for language, the problem is that in order to have a good enough simulator of language, you have to already have the model. So you have this chicken and egg problem, right? Because it's not compositional like physics is. Here's the big trend. Buying private data. Buying the data that's not on the internet, right? Buying data that's not public. If I had to guess out of these different options, this is where the next 1,000 times more data is going to come from. It's easy to overlook this because the data that we see is the stuff that's online, right? But the largest data sets in the world are the stuff that's offline, the stuff that is too valuable or too sensitive or too important to just make generally available. And even the stuff that was online is being pulled offline by companies who would rather make money from selling access to the data for training AI models than give it away for free and spend a bunch of money on their servers while people are banging them with big scrapers all the time. That makes sense. But there's a problem. Private data sets are really, really hard to get access to. Think medical records and government statistical data, or video cameras, or audio data sets from translators, all sorts of stuff. And it's hard, and it should be hard. Why? Because it's also ethically a lot more spicy, right? It is hard, and it should be hard, right? In a lot of ways. It needs to be protected. It needs to be ethically stewarded. So let's talk about this. Let's say an AI researcher wanted to approach a big data company and say, hey, I'd like access to your data. What happens? Hi, I'm so-and-so from AI Company Incorporated. I want to train an algorithm on your data. Can I do this, please? Hi, I'm the company's lawyer. Your project is awesome, but I don't think I can send you the data because you might use it for another purpose that gets us into legal trouble, right? Big problem. Next one. Hi, I'm Jovita's chief privacy officer, and I think your project is great. But if we sent the data, you'd also be able to use it to invade the privacy of our users. Not cool. Hi, I'm the Chief Information Security Officer, and if I'm going to give you a copy of our super secret sensitive data, you're going to put it into a computing system that I don't control. How do I know that my data is safe? Right? It keeps going. Hi, I'm the Trust and Safety Team. Or like, hi, I'm the Chief Executive Officer, and I think your product is great. But if we sent you the data, you could use the data to build a competitive business. I think this is actually the real kicker. Because laws kind of linger behind. They're kind of, they're sort of, I don't think laws have totally caught up with the AI revolution yet. And if you look at why social media companies shut down their stuff for scraping, if you look at why news organizations shut down their stuff from scraping, if you look at why the data disappears, if you look at why academics sometimes keep their data to themselves, because they want the competitive advantage. They want the action. And if you give a copy to someone else, they're going to do whatever they want with it, and they never have to call you again. Not cool. So I think there's an opportunity for 1,000 times more data for the next big AI revolution to certainly be over there, but there's a set of big problems standing in our way. So how do we solve those problems? Let's summarize the problem. In order to train an AI model on someone else's data, an AI product or safety researcher needs to obtain a copy of the data for training. And that triggers legitimate privacy, security, IP, legal, and adversarial concerns. These are correct. These people are protecting the interests of this data and the interests of their company and the interests of the people about whom the data is concerned, right? It's important. Let's talk about a different paradigm. I'm going to tell you about a library called PySift. For the last little over 7 years, the OpenMind community has been working on this problem and putting it into our flagship library called PySift. Let me show you how it works. So you have a researcher, they want to work with an organization. That organization launches what's called a data site. Data site is like an Apache web server, but for private data. For Apache web server, a web server is the way the internet works. Like you have a server, that server has files in it, and it's on the internet. And when you click a link, what actually happens, like a simplified version of what happens is that server, your browser goes out to the server, downloads the files that are in the server for google.com or facebook.com or whatever, and your browser knows how to show them to you, right? The internet works by you downloading data. A data site, instead of a website, is different in one way. Instead of you downloading the data, you can download answers to specific questions based on the data. You can download a trained model or a prediction or whatever based on the data without downloading the underlying data. Let me show you the kind of the cartoon character version of how this works. Okay, so organization has their own data site, just like they'd have a website, right? They load their algorithm into the server, they create an account for an external researcher, and then they go and have a coffee, right? Just like when you have a website, right? You don't babysit every single person that comes by. Okay, researcher comes in, logs into the server, and sends some code into the server and says, hey, I want to run this code on your data. Can I do that? And there's this whole category of algorithms that come from a bunch of different fields. They have this loose umbrella term called privacy enhancing technologies. I personally feel they should have been called that. They should have been called information governance technologies, because what they can allow the data site to do, like if you look at the framings of these papers, is to automate the enforcement of some type of policy on a data. Like to automate the enforcement of use versus misuse, to automate the enforcement so that the data administrator can be off having a coffee somewhere while this server knows how to respond appropriately. If that makes sense. They're about scale. We won't talk about them too much today, but we can on a different day. So they upload their code, they generate the answers. The organization administrator, maybe they get really hands-on, they review the code, right? And it gets approved, either because the administrator looked at it or because the administrator had an automatic policy that allowed for the approval to happen. And then the external researcher can download the result of their computation, the data science answers or a slightly smarter model or whatever the case might be, right? Now, this server doesn't exist by itself, right? It exists inside of networks. A network is just like, think of it like a registry for kind of search and discovery. It's just sort of like, like DNS is to the internet or like search is to the internet, and network is to data sites, if that makes sense. So the kind of cartoon character version of this is a researcher can submit their science project with their code and all this kind of stuff through the network to the individual data sites. Some of them approve the project, some of them don't approve the project. And then once the ones that approved it, the AI researcher can remotely send their code down and start running experiments. Again, without ever asking to download a copy of the data, right? And every single use of that data is approved by the owners of the data sites. Does that make sense? Okay. Let's see how it works. Oh, different. It's not different from federated learning. So federated learning is like a special case of this. I'm giving you kind of the more general version than federated learning, but highly related to federated learning. Great question. Great question. Okay, so now I'm going to stop sharing the screen, and I'm going to share another screen, which is this one. Let's see. I think I probably need to make this bigger, don't I? Is that big enough? You see that? Awesome. Cool. Getting close, and we'll have time to do questions too. All right, so I'm going to install the latest version of PySift. Cool. Installing. Great. Import Sift as Sci. Importing this library. Oh, I might need to zoom out in a second. I'm not sure. Sci.datasites. These are servers on the internet. Okay. Each of these are holding data somewhere. There's a registry here where people register basically what servers they have, if that makes sense. So they can kind of show up conveniently in this little lookup table. So now I have one Trask personal. So cert. Okay, here we go. So that's me. So now I'm going to grab that one. This creates a guest login. So I'm not logged in yet, but this is a server that I have deployed in the cloud somewhere. It's holding some data. Let's see what's on it. So we're going to go Trask here. Cool. Great. Trask.datasets. What do we got? Netflix. So I went last night preparing for this talk. I went online and I downloaded my Netflix watch history. It's in this server because I wanted to show you this. Cool. So this is stuff that I've watched on Netflix. I don't watch Netflix all the time, but I do enjoy Netflix. I've lately gotten into, Peacock, watching the Olympics. It's been great. So what I want to show you is just the cartoon Hello World version of how to use this stuff. You can do way more complicated things than what I'm about to show you, but like I want to sort of show just the very basics. So what's the first thing we need to do? We need to create an account. Okay, so we're going to create an account. I'm going to create an account with my OpenMind email. So I'm going to guest client. Sorry, I called this Trask, didn't I? Whoa. We'll create a password. We'll confirm the password. Cool. We now have a new account. No, I don't want to save the password. Thank you. All right. What's next? So let's log in. So it's asking me for a password again. All right, now we're logged in. So now this variable that I have is pointing towards the server that has been deployed that has my Netflix data in it. Okay. So now what happens next? So we're going to go to datasets, which was Netflix. Let's select Netflix dataset. Cool. We can see it's got assets, so it only has one asset. So basically, you can think of a dataset like this metadata plus a dictionary of stuff, if that makes sense. So it's not super complicated, right? So we'll say this is the Netflix equals this. If we want to see the assets, we can go in here. So we have watch history as an asset. If we want to see the specific asset, you can do this. So again, it's just like nested dictionaries with some extra metadata. Okay. So now we'll say this is watch history. How are we going to write code that does something with this? Well, the way that this works is there's a mock data set. This is fake, but has the same number of rows and columns and same internal structure as the real data. So if I write code against this fake thing, it's going to work if I ask them to run it on the real thing. If that makes sense. Not a complicated paradigm. It's simple, right? Not rocket science, right? The infrastructure required to do it well, considerably more difficult. But the interface is you have a fake version of an API locally. You can write code against that. You can send that to the real API, which gets reviewed. So let's do that. So I've got a little for loop here that just like counts the number of times that, oh wait, mock, did I call this mock? Oh, let's create mock. Mock equals that, mock, great. We do this, and num watches is 133. Cool, because this was all fake on the mock data, right? So let's submit it to run on the real data. Fortunately, we're short on time, so I'm not going to be able to explain all this. But what I do is I create a method. I have this decorator. The input policy says, what variables am I allowed to run this on in the future? I'm asking to add an API endpoint to the server that I can then call in the future, if that makes sense. So the server ships with some APIs. I want a custom one that does this thing, and it's going to measure how many times I watch Star Trek, right? Because I like Star Trek, and Star Trek is cool. Make sure I did all the variables right. So I called this watch history is actually what we want. Oh, that's fine. That actually would have worked fine. Great. So we created our function. Great. We created it successfully. And now I'm going to go. So what was the name of my client? So got my client. And the way that I submit this, go client.code.request code execution, right? Count watches. Great. Successfully submitted. Now, let's look at my requests. Ooh, pending, still waiting. Okay, so I got to wait for the review to happen. Well, it turns out I am the data owner, so I can approve this request relatively quickly, which is nice. If we have more time, I can go through other ways in which this can be use differential privacy or whatever to be able to automatically triage these things, but we're keeping it simple today. So I'm gonna run it again. Approved! Yay! We can run our stuff. Fantastic. Client.code. Count watches. Look, it got added. Perfect. And what was the name of our argument? It was watch history. So watch history equals, and what did we want to pass in? We wanted to pass in a private data set that was watch history. Perfect. Boom, 8. I watched it 8 times. Cool. Not crazy complicated. And the argument that I would make to you is that because people want to maintain control over their data, right? If they can, they will bring more of it to market, and more of it will become available. And in my opinion, the next big breakthrough in AI is going to come from 1,000 times more data showing up in interfaces just like this. Cool. If you want to check this out and play around with this kind of stuff, you can go to docs.openmind.org. Actually, I should put that in the channel. So we just released a new version of this yesterday. If you want to check out, if you have questions or want help, you can go to our Slack and get an account and go to the support channel. So #support, it should add to that automatically if you want to play around with this kind of stuff. Feel free to submit code requests to my Netflix data set if you want to play around with it. The server will be up in the future. You can see if you can figure out what other things I like to watch. That's fun. Cool. That was really what I wanted to show you, is that basically AI breakthroughs come from huge jumps in data. I don't see other places where there might be a huge jump in data except for this one. And I think the companies are already trying to go find non-public data sets. And I think this is going to be a bigger, better, faster way that they do it. Cool. I guess we have a couple minutes left for questions. Anyone have any burning questions that I can help answer?
There's a few in the channel already.
Awesome.
I think there's some hands raised. So I'll let you moderate this. It seems like you're on top of it.
Okay, fantastic. Super interesting for use cases of compliance reporting supervisory technology, wherein supervised entities are data sites and public sector authorities, other requester running algorithms over the data. Totally agree. Sort of an analog for so-called pull APIs. So the combo for a long time, but this library seems super nice for consolidating the combo and codified for. Matt, totally agree. If you want, there's a whole other talk we could do about like open source versus closed source, and like open source is like very difficult to prevent misuse, and closed source is like it's all in one place. What are we doing? Like big other types of problems. This stuff is like a really interesting hybrid between the two, in my opinion. Like there's lots of really interesting things there, but that'd be a different talk for a different day. But totally agree, Matt. Really interesting. Abin, Andrew, forgive me, but what all pets are in SIFT? It seems like a demo of federated learning, but something tells me it must have incorporated privacy as well, or input-output privacy verification as well. Oh, brilliant. So Evan, I decided to keep it crazy simple today, just with like a simple code submission. But if you wanted to do output privacy, for example, the code that you would have submitted would have had differential privacy stuff in it. So it can pull in a differential privacy library. We've also from time to time worked on automatic differential privacy systems that can like analyze your code and automatically add differential privacy in different areas. This stuff still needs more work. It's not because like the differential privacy theory is far enough along, but the engineering to get it to work well is still something that's an ongoing project. Yogi, you had a your hand up.
Thank you. Sorry, I was being very lazy with not typing out. I'm really intrigued by this because it feels like you're taking private data sets that people are willing to make public so that they can use them. But there's already quite a lot of websites like Zenodo where researchers for years have publicly said, here's my data set, go with it. Do you think there's some way that they could become perhaps a bit more complementary? Because I love what the premise is, to get that private data out safely, but I would be very sad, especially as someone that has put data on Zenodo, that if the stuff that is already public wouldn't then be used, because the intention and the sharing and that type of thing is in there, particularly given all the conversations about ethical AI and fairness and bias in models. A lot of that work could potentially be learned from the data sets that have been shared already, to then further improve potentially, because you talked about the quality of the data as well as the quantity. So that's not a very specific question, but that's kind of where my mind was at, and I wondered what you were thinking in that space.
Totally agree. There is still a big, wide open space for data sets to be just totally open. This is like no commentary on that. And so I think that this is a yes and conversation. There's a lot of data sets that some data sets that maybe shouldn't be open that are. Like, I think there's like some that and there's a lot of data that just doesn't get used at all. And that causes all sorts of problems, like everything from, hallucinations because the model didn't have awareness of a certain area, to bias problems because certain groups are underrepresented because their data is kept too secret, and all kinds of lots and lots of problems that can be helped with that. But this is in no means trying to say that all data should be locked down or something like that. By no means. That would not make things better, I don't think. I can also hang out for a little longer. So Krish, what's up, man?
Hey, Andrew. Great, man. It's always great to hear you out.
Oh,
so I know we have to catch up, but I thought to put up a quick question over here, but among the entire community. We have been looking into, and there have been a lot of development recently in the past few months. I know what you have been doing in OpenMind and always been championing that, but we have seen a lot of recent development. Recently, Google DeepMind and Prime Intellect, they worked on something called DiLoco, where they're looking into decentralized AI computation. So why don't you talk about it from an OpenMind's perspective, that in the coming future months, I would not say years, but the future months, how do you perceive decentralization AI, where you have different compute resources, and as you say, right, we take the data to a resource, so how can we again use these compute resources to train a large LLM or a large model?
Right. So much change is coming. And it's a great question. So I think the shortest way I can respond is just to give the basic ingredients of change. So the first big ingredient is you need to have data co-located with compute. And so this is also an interface for accessing other people's compute implicitly, right? So that's a big thing. So, and if you think about there's an interesting synergy with the early days of the internet. The internet was originally prototyped to be a compute sharing infrastructure. I don't know if people know this, but that will also be an element of this as well. And the second one is GPU enclaves. GPU enclaves are so cool. The H100s from NVIDIA, they shipped with the hardware that was required for enclaves, but some of the drivers are still being finished. But the cool thing about a GPU enclave is that if you wanted to use data from one party, but they aren't comfortable with putting that in someone else's data center, a GPU enclave can solve that problem because it provides these attestations and privacy where the person who's running the computer doesn't have unilateral control over all the data that's in the computer because of the way the chip is constructed. That's too short for that to be really a good explanation, but if it sounds roughly interesting, go Google it, and it's really cool. Maybe we'll but yeah, big changes. Jekaterina.
Hi, yeah, thanks for the presentation. It was great. I think I'm gonna mostly refer to the beginning of the presentation about talking the big picture. So the main thing was more data. Doubtly that we're gonna do anything about the algorithm. What do you think, if we can understand how neural networks learn, does that mean we would still need more data?
I think that if we figured out how neural networks learn, what we would find is that a tremendous amount of the learning process is redundant. There's a lot of elements where the neural net is relearning something that it already knows. And if we had the ability to map that out, we could skip that part of the training, which allows learning to happen basically much. We don't waste time on data points that aren't actually helping, and we can skip to the ones that are. I think distillation is actually already kind of doing this internal, to be honest. So I think that if we get that understanding and that structure, it unlocks a lot of really interesting stuff. And I would also put that as like a little bit of a hybrid, because if you can get better data points by throwing out the ones that don't matter, either at the beginning of the network, even inside the network in like a dropout like way, you can learn faster, and that is both better sample complexity and in a way more samples. If that makes
So
sense.
you think the first steps would be figuring out what doesn't matter actually?
So if we're following the theme of a recent theme in the last 10 years of where big innovations come from, like figuring out where redundant learning is happening is often a very, very good strategy. You could even look at convolutions as a way of doing that. Convolutions are like, hey, you have to relearn corners and edges at every single individual place in the neural net. What if you just learned it once and slid that piece around so that one set of weights, right, is always responsible for learning the same pattern? That's actually also kind of a data strategy, because it means that a smaller number of weights has more training examples. When you're sliding that around, that from the perspective of the weights is another sample that it gets to look at, if that makes sense. So the more that we know about how models learn, the more strategies like that we can employ that improve the number of the sample to weight ratio, if that makes sense.
Yeah, thanks.
Yeah, great question. Any other more questions, or we can call it a day? Oh, Caitlin, how does this address the competitive advantage argument? By making my data available, I'm still losing my competitive advantage. Very interesting question, Caitlin. I don't have time to get into all of that, but it's the right question. That comes down to, so basically I would say step one is don't give other people copies of your data, because you don't need to anymore, and they don't need you to either, if that makes sense, right? Step two is then when they pull out individual computations, right, or individual analytical results, like what are you comfortable letting them pull out? Is it a very general purpose model that can do all sorts of things without talking to you? Or in the case of GPU enclaves do this really amazing thing, which I didn't really get into today, but they make it so that multiple people can have shared control over a computer and everything that's in it. You can imagine a world where, if, say, 10,000 people train a model together, 10,000 people each get veto power over what that model is used for. Now, that veto power you might lose for a lot of things. The main one you might use it for is charging money, if that makes sense, right? Lots and lots of big open questions. Those are overly simplistic examples, right? Those are overly simplistic examples. There's big, wide open space answering that question, Caitlin. And I think that as that question gets worked out, it's going to fix a lot of broken incentives in the market for information. And when you fix broken incentives and you make a market more efficient, more resources show up, and we get better, stronger AI models. So that's like the shortest possible way I think I can probably respond to that, but it's the right question. There's a lot of really, really interesting work to be done there. Milan, what if a huge number of requests are sent to one organization through this library? Will they be able to handle the requests? Fantastic question. This is what privacy-enhancing technologies are actually for. Privacy-enhancing technologies don't necessarily change your standard of privacy. And organizations don't really want to change their standard of privacy. They have some moral, ethical standards they're already operating with, and a set of laws are operating with it. What they want is increased scale in triaging requests. Now, to give you a cartoon version of what I mean by this, think about synthetic data. Has anyone heard of synthetic data before? It's like a privacy-enhancing technology. Synthetic data is where I take a data set and I try to make it impossible to answer some questions from it while making it still possible to answer other questions from it. So, hopefully you can't learn, like, if it's a medical data set, you can't learn whether one person has cancer, but you can still learn what causes cancer. That's like what it does. So you hand that data set to someone else. You do lose a bunch of competitive advantage. So Caitlin's right? Like, now they can use that data set for whatever they want, building products, blah, blah, blah. So it doesn't solve everything. But synthetic data does solve is now I don't have to triage a bunch of questions about this data set as long as that dividing line is okay. So pets are not a panacea, but they each propose some type of automatic enforcement for some type of policy you're trying to enforce, if that makes sense. So basically the answer is pets. That's what pets are actually about. They could have been called like scalable information governance technologies, but they were called privacy enhanced technologies instead. That's fine. Privacy is great. But I think this it could have been more precisely defined somewhere else. What has been the organization's response to this idea so far? The organizations? Which organizations? We'll come back to that. How can startups and smaller companies gain access to the resources needed for AI innovation? Okay, maybe I probably should have finished with this. If you want data from someone, and first you ask them for a copy and they say no, ask them to deploy one of these servers. They're free. It's freely available open source stuff, Apache 2 licensed. All the work they have to do is launch effectively a website and create a fake version of their data set or model, right? It's not that much work, right? And then you can propose your computation on it and they can hit approve and you can do your thing. So that's the new paradigm. The new paradigm is, instead of asking for a copy, ask for the ability to submit code requests to their thing. Ask them to extend their website with one more endpoint, if that makes sense. Cool. I think we're probably there. Any other burning questions before we go? Awesome.
Okay, thank you so much for the talk and for staying a little bit over and answering all the questions. It was a really great discussion, presentation, everything.
Awesome. Thank you so much for being here. Thank you for all your time and attention. Come hang out in Slack sometime. Feel free to say hi. My username is at Trask in Slack. Play around with my Netflix data if you want to. If you have any issues, drop in a support and say hi. Have a good day.